Okay, how's everyone doing today? Good? No more tests? You all done?
I just took it.
Ah. Hope it's going well. Everyone's staying nice and healthy. That is. So, oops, I apologize, everybody. So, today, we're going to wrap up everything we will need for magnetism. The homework is due next Thursday, which will actually be the next class day we see each other. Before we get started, does anyone have any questions?
I
That's not right.
emailed a lot to you. Do you want me to
Yes.
print it off or is that fine?
Email is just fine.
Okay.
Wait, does next Thursday mean next week's Thursday?
Correct. Next week's Thursday. The Thursday that happens next. Where is my mouse? It's in my office, isn't it? Shall we do?
The eraser's behind your computer.
No wonder I haven't found it in 2 days. Thank you. All right, so when it comes to magnets, yesterday we looked at the magnetic field produced by wires when they run current through them, which contributes to the fact that wires are susceptible to magnetic fields when there's electric current running through them. I believe we worked that 2-wire example and then we broke for the day. Okay. We talked about this, didn't we? Did I show you this?
It didn't have a circle at the end.
Oh, that's just to represent that it's rotate, that it can rotate. Okay. Be a little more repetitive than I thought it were.
Oh, yeah, we did this and then we went.
Okay, that is fine, that is fine. You're okay, actually, then. So. Any questions before we begin? Okay, so let's close out magnets and then get on to our weekend. Yesterday, yes, we looked at the case where all the magnetic cases involving electric current running through wire. And all those rules still hold true for if the wire is just bent into a not straight shape and still applied a magnetic field. What ends up happening though is, if, say, you bend your current wire into a not straight shape, the force from the magnetic field will point in different directions on different part of the loop. And if it is allowed an axis of rotation, it will begin rotating. And this is the principle that fuels most electric motors and subsequently electric generators as well. Because if instead of running current through the wire and letting the magnet turn the loop, you could instead crank the loop by hand, like maybe put a handle on it or a water wheel and just crank, and that, because you're now spinning it through a magnetic field, would create electric current in the wire. So a motor and a generator are the same machine, just run backwards. we're actually going to build one of these in a couple of weeks when we have our last lab for the semester. So we're going to go ahead and do a little bit of the math involved in that. There's going to be a lot of formula on screen in a second. I have put the only part you need to care about right now in a little gold box. The rest of it is hypertext. All of this is to describe how, when you run a current through some loop or square of wire that has a surface area, so in the case of this rectangle we were looking at yesterday, it occupies an area of space based on the dimensions of the rectangle. You could make it a circle and it would be the area the circle takes up. When you run a current through a wire that is bent in such a way that it has a surface area, and then you project a magnetic field perpendicularly through that surface area, and lastly, factoring in the number of loops in that wire coil, you will get a torque on that wire. I'll put that formula up over here and re-specify all of those terms. Torque equals current times area times magnetic field. I like to say magnetic field perpendicular to the area instead of the other way around. And then times number of loops in your wire shape. First term is torque. This is the same torque you have used in physics class past. Torque is the angular equivalent to force. Normal linear force makes things accelerate in normal linear straight lines. Angular force makes things rotate. So because of the force pointing in different directions, and if the thing is allowed to rotate, since the force is making it spin, being applied at some distance from the axis of rotation, it is technically a torque being produced. And so that is a term in the formula. We could plug in the formula for torque to find the force, though. That is a possibility. Next, current. Just the amount of current running through the wire, still measured in amps. A is the surface area, measured in meters squared. B, magnetic field. That needs to be perpendicular to the surface area. Magnetic field needs to actually pass through the shape. And then lastly, N, number of loops in the wire. As this has been drawn, this motor would only have one loop because the wire just goes through the field one time. But I could, if I wanted to, bend it in such a way that the wire doubles back around a few times before coming back out, and the number of times it goes back through is the number of loops. And because of the way the formula works, number of loops is just a straight multiplier. The more loops you put into your motor, the more torque you'll get out of it. So physically, the more wires you can cram in there, the better the machine is going to be. Similarly, if you want to increase the power, you can increase the current. You could increase the size of the loop, although depending on how big your machine is allowed to be, that's kind of a limiting factor. But you could if you wanted a more powerful one, and you could also crank up the magnetism. All of those things, when increased, make the motor more powerful. I think the most cost-effective and space-efficient way of increasing the torque, though, is just the number of loops. So, the motor's in, say, an electric car. When you push your push your foot down harder on the gas pedal, you're just increasing the current to the motors. That increases the torque the motors exert on the wheels, makes the wheels spin faster.
How does it increase the current?
I'd say a simple version of the circuit would be if the pedal was connected to a variable resistance resistor, and by pushing the pedal, you are decreasing the resistance of that component, or telling the system to decrease the resistance in the part of the circuit that will feed current to the motors. So, this is a pretty good mock-up of what we're actually going to build in lab in 2 weeks, 3 weeks. So let's say someone has made this wire circle. It's only one loop, so n will equal 1. They are running a current of 2 amps through that wire circle. It has a radius of 1 meter, and the magnetic field passing through the loop is equal to half a Tesla. It is worth noting, however, that this magnetic field is at an angle. It is not perfectly perpendicular to the surface, the plane formed by the loop. So do I still have a function for orange marker? Doesn't look like I do. Right. I'm going to redraw this picture from a different angle. 3D perspective is nice, but it makes graphing, like dividing up into vectors, just a little bit harder. So I'm going to redraw this picture from the side, as if we were looking down the length of the x-axis. Can you guys see how it's just the same picture tilted?
I don't even see the difference.
You don't see the difference?
Well, I looked at this, it's, yeah. Like, were you just drawing like the X and Y planes and then the magnetic field points?
Yes, I drew it this way just to make it a little easier to show that we need to divide the magnetic field up into its X and Y components. Because for this type of a motor, only the field passing through the loop perpendicularly will actually matter, and of this particular vector, this magnetic field line, only its Y component is actually perpendicular to the loop itself.
Oh, so is that like orange horizontal line, kind of like that part of the circle where it is perpendicular?
Correct. So this is meant to be, I tried to use the same colors. Orange is the wire loop, and I've just tilted the camera from this 3D view to a 2-dimensional view coming in through the x-axis. We've just tilted the camera so that the flat loop is now just a 2D line, or a 1D line. From this perspective, we can see that only the Y component of the magnetic field is actually perpendicular to the loop, so we need that Y component. So, a little bit of trig time. We know 30 degrees, we know hypotenuse, we want the leg that is adjacent to 30 degrees. That's going to be cosine. Cosine of 30 will equal the Y leg over half a Tesla. My memory serves, please let me know if I'm wrong. That should give us Y equals 0.43 Tesla. keep working, just need to change something on the slide. So to find the torque on the loop in this starting position, rewording the question, make a little more sense, I apologize. To find the torque on the loop from its starting position, we need to know how much magnetic field is currently perpendicular to the loop. Once we've done that, we now have all variables that we need. So, torque equals current times area times perpendicular field times number of loops. Torque is what we want. Our current is 2 amps. Our area, this is a circle, so we need area of a circle. That should just be pi r squared. And thankfully the r is 1 meter, so that's pretty simple. B, we have our perpendicular B field, 0.43. And for simplicity's sake, this is just one loop.
Oh, wait. Wait, why did you put 0.43? I'm just kidding.
Let's finish that up in your notes. I'm going to see if something currently needs to back closet. All right, what kind of torque are we looking at?
2.7.
Nice. And what are the units of torque?
The Newton.
Newtons times meters, correct. All right. So the torque in this current location, wait, was it 2.47?
Just 7.
2.7. Thank you. Newton meters. Very good. That is the starting torque in this position. Now, this torque is going to make the loop begin spinning. And for this particular system, the loop's axis of rotation is the x-axis. So, from this perspective, that means it's going to spin through this axis, kind of to and fro like that. From this angle, we're kind of looking down along the x-axis, so it's going to begin rotating from this angle clockwise.
Can you repeat that?
Right now, the way that I've positioned this, we're looking down the length of the x-axis. Yes, my intention with this picture is, I don't much care for the way this picture is labeled in terms of which axis is which, but from this picture, the side view that I've drawn the second picture from is looking down the x-axis. This picture is drawn like you were standing here looking towards the origin. Which means that your line of sight is the x-axis, and it's going to begin spinning clockwise along this axis of rotation.
So if that's the X, what's the other one?
this picture has labeled this as Y and this as Z, which I don't necessarily agree with, but
This is hard to visualize.
one second. Yeah, I think it came into the bottom.
Oh my god, I remember this.
But heroic or is rather beefed up bike that he was using. Okay, so I was looking for a hula hoop. This is just gonna have to do. As drawn in this picture, the loop is currently oriented like this.
Oh my god, it's to the side?
Yes.
Wait, how was I supposed to know that?
Years of steering and graphs.
Is it because of the magnetic field coming out like that?
The magnetic field would, if this is the z-axis, the magnetic field would be coming out this way.
Okay. So like I wouldn't really know that it was positioned like that. Like how do I know that?
A lot of trial and error working with graphs over the years. Sorry. That's why I'm trying to help illustrate the point. So, in this picture, the wheel is oriented like this. The magnetic field points this way, and the wheel can rotate through the x-axis like this. That's chaotic. In this picture, I've just changed the angle so that the wheel is like this and will rotate this way. Does that help?
Yeah. Okay.
Okay.
Wait, okay. Wait, oh, one more time. Why did I know that it would rotate that way?
Because the x-axis is the axis of rotation. That is the axis it's going to spin around.
But like, didn't we say that we were, okay, we're looking at it down the x-axis, right?
Yes, correct.
And so you are rotating clockwise on the x-axis,
Yes.
which is, yeah. Okay. I get it. But like, why did I know it was clockwise, not counter? Just because your magnetic field is that way?
Yes.
Okay.
Counterclockwise or clockwise isn't super important right now. What is important is, as it begins spinning, the amount of field that is perpendicular to the field is going to, sorry, the amount of field perpendicular to the loop is going to change. Because if this was to begin rotating and now it was angled this way, if it had spun and was the wheel, the loop, was now oriented vertically, suddenly the x component of the field would be what's perpendicular to it. So as these loops spin, the amount of perpendicular field changes. And eventually, when the wheel is completely within, completely parallel to the magnetic field, none of the field is perpendicular and the torque drops to zero.
Like, in that moment in time, it's not moving like that?
In this moment, there would no longer be a force pushing. The wheel's momentum would try to keep it spinning forward, but once we then enter, like if the momentum carries us past that point, now the field is going to try to push us back the other way. If you were to build this machine and just leave it turned on, the field would push the wheel here and try to keep it there. It wouldn't actually rotate, since the torque changes based on its position.
So then how do you make it rotate?
Well, what the motor actually looks like on the inside is something like this. We have a loop spinning around inside of a magnetic field. The magnetic field is provided by this bar magnet with a hole in it, basically. And the wire loop is connected to a power source that usually has some sort of a split in it. And when the loop passes through or passes over that split, the power shuts off. The circuit is broken. Because if when the wheel gets to this point, there's no longer any current in it, there won't be any torque anymore. So the wheel's momentum will just keep carrying it through. Then, once it's gone around and is in a position to accelerate again, the current will come back on and the torque will accelerate it through another cycle. And this will be better illustrated when we build this type of motor together. For this system to work as advertised in the sample question and in the picture on screen right now, the power has to shut off periodically. It needs a built-in way to cut the current going to the loop so that its momentum carries it through the part that would stop it, and then you turn it back on so that it accelerates again. And we will demonstrate that more in a couple of weeks. But that is the basic principle behind most electric motors. And with that, that is, I think, all of the important things to know, things that will be on your homework. I do have one more thing that I want to show you, because I have a couple of machines to demonstrate what it can do. A machine and a pipe. So, I briefly want to talk about something that you've probably never heard of before. You've heard of magnets, you've heard of electricity, you've heard of motors, you've heard of generators. You might not have heard of magnetic flux. Do write it down just in case, but I'm not planning on doing any grades based on it. I didn't show the other class yet. When a magnetic field passes through a solid object, a certain amount of magnetic flux is produced. Flux is a very strange concept. It exists, it does very weird things when it exists, and it exists when a magnetic field passes through something. But only when the field passes perpendicularly through a surface. If the field is parallel to the surface, nothing happens. But when a magnetic field passes through a surface, flux is produced. And when you make or change magnetic flux a lot in a very short amount of time, the universe kind of has a seizure, which further contributes to why physicists don't really know what magnetism is. To demonstrate this, I have an aluminum pipe. This is aluminum, and aluminum is not magnetic at all. To evidence that, nothing. Got two more magnets over here. Nothing. Meanwhile, So these magnets all work, this just isn't magnetic. The first thing, I'm going to drop through this particular pipe. I already dropped it, now I can't find it. Ah. This is an iron, or maybe brass, mass. It's just a piece of metal. It is not magnetized. I'm going to drop it through, and it will behave normally as one would expect a falling object to behave. So it takes a little less than a second to fall through. I'm now going to drop this magnet through. And again, remember, aluminum isn't magnetic. So it should just fall at the same rate, right? It should. No. It's not a very strong magnet.
Do the little one.
Hang on. I can't afford for this magnet to hit the ground, it'll weaken it. Okay, ready? Fine, it's still not strong enough. Okay, so note to self, I need a stronger magnet for this part of the demo to work right. What happens as the magnet falls through the aluminum is, when the magnet is in the aluminum, a certain amount of flux is produced, because there's now a magnetic field passing through the wall of the aluminum. And as the magnet falls, the flux changes because the magnetic field changes. And the universe doesn't really like that.
I don't get what flux is though.
No one does. Which is why I'm not very honest. I think that takes about a fraction of a second longer than the other one.
What was saying?
Okay. So, teacher needs better magnets. That's pretty clear. I know this thing works though. Bless you. So, this is an electromagnet. We've got an iron core. We've got a copper cable that the electricity is going to pass through. And it's connected to an AC generator, alternating current. That means the current put through this coil is going to invert back and forth every nanosecond. It's going to switch back and forth very quickly. And when you run current through a wire, especially when that wire is wrapped around an iron core, you have an electromagnet. So this is going to produce an electromagnet with it, and its field is going to constantly be switching directions because the direction of the current is going to constantly switch directions. As proof, when it's not turned on, it is not magnetic. When I flip this switch, come on, something needs to work there today. There we go. It is only magnetic when the switch is on. Now, this, still aluminum, not magnetic at all. But when you force a changing magnetic field through an object, and that field changes, weird stuff starts happening.
Was that flux?
That was flux. That is what happens when flux changes very quickly. Because since this is an AC generator, the magnetic field keeps changing constantly. That means that the flux passing through this ring changes constantly when I turn it on. And when flux changes, the universe has an aneurysm and does weird stuff like that. This isn't magnetic. It shouldn't be pushed around by a magnet. And so if I had stronger magnets, putting a magnet down that aluminum pipe, it should have fallen more slowly, because when flux changes, a force is produced. For this particular machine, that force just pushes it upwards.
And the other one wouldn't be like attracted?
No, it would just be fighting gravity.
Oh, it was trying to go up. Like if you, I mean, that's why it was slower.
Right. It would be slower if there was a field force from the flux that happened to be fighting against gravity. Since the magnet would be falling down, the universe would try to resist that, and it would push the magnet up, or it would try to. Gravity would still win, it would just fall slower. All of this is just to evidence that magnets are weird, and they do some very strange things that we don't always completely understand. Like, why is a non-magnetic object flying around because of a magnetic field?
Okay, this might be dumb, but a magnet, for something to be a magnet, you need two different like materials that are magnetic to each other, or how does that work?
To have a magnet?
Like, okay, yeah, so iron is magnetic, right?
Correct.
And so like a piece of iron isn't a magnet.
Not by itself.
So what,
This, by itself, this iron core, not a magnet. It's just a piece of iron.
yeah. So then what made it a magnetic, I guess? You know what I'm saying?
Yes. So, all man-made magnets happen when an object's particles, like its electrically charged particles, its protons and electrons, are forced to realign in such a way that it produces a magnetic field. Normally, in conductive metals like iron, the electrons are just kind of free to do whatever they want. They're just constantly zapping around the inside of the object, being shared across every iron atom. But when you expose this to a magnetic field, that field forces all of the electrons to form into a specific pattern with the electrons that produces a magnetic field of its own, and then you get the magnetic force between this and the original magnet, now that they both have.
Because of the two fields?
Correct. And to show that, let's see if I can make this work. So putting this magnet near this iron forces the iron's particles to arrange in such a way that it now makes its own magnetic field. So only when this magnet is attached to the iron does it actually have any magnetic properties to pick up this paper clip.
What is the paper clip made out of?
Also iron,
Okay.
or maybe tin, probably iron. There we go. So right now, the permanent magnet is making the iron a temporary magnet, and removing the permanent magnet, the iron loses its magnetic field. Inside of this electromagnet, when the current passes through this cable, whenever current passes through any wire, the wire makes a magnetic field. That magnetic field forces this iron to produce a magnetic field. So the entire piece of iron acts like a magnet for that split second.
So for a magnet, there has to be two different materials that produce a magnetic field?
Well,
It can't just be like one material?
it can. Where's my cruddy little disc magnets? So this, actually, here we go. I'm going to go with this because it's easier to see. This is is man-made. This was not dug out of the earth in its current state. These things, you buy them at the hardware store, you probably played with them in science class before. These are iron clay disc magnets. These were made when a human took clay, put in iron dust, fired it in a kiln, and made it into a magnet. The iron in question was not a magnet beforehand. What they did was, when they were making this and mixing it and firing it into a solid clay shape, they exposed it to a separate magnet while that was happening. And since it set in place while exposed to that magnetic field, that locked its particles in the positions needed for this to keep producing a magnetic field. Which is why this one's field is always on, but also why it can be damaged and lose its magnetic field over time.
Well, I don't understand why you lose it.
Well, every time I drop this and physically hit something, its particles get scrambled. And its particles being in very specific locations is the only reason this is a magnet right now. So whenever you drop one of these man-made magnets, it gets weaker. Its particles just get scrambled and more scrambled and more scrambled until it is now just a normal piece of iron again.
What about earth-made magnets?
Those are usually stronger because they were forged from the magnetic field in Earth's core, but would assume the same principle would apply. Hit them enough times, they'll lose their powers. Excuse me. Some materials make better magnets than others, though. The best magnets I've ever been able to buy at Lowe's are neodymium. They're very small, kind of silvery. They were strong enough to where if I held them, they got this far apart. The ones I bought are flat discs, but they were strong enough to where held about this far apart, they would rip themselves together at a high enough speed to break themselves. They're very strong. I've managed to get them to stick on either side of my hand before, no problem. And then I would pretend to be Iron Man and pick things up. Because I was and still am a child. Main takeaway I want to show you from this is that magnets are weird. And despite everything that we've talked about, all the things we do understand about them, there's a lot we still don't. And so that is professional license from me, a professional physicist, to be confused with all of this. Because it is confusing. And it will remain confusing until the end of the universe and we finally get some answers from hopefully the being who made it. Additionally, you are right. For this electromagnet to work, you do need the iron. Take it out. It's weaker when I take it out, but it's the coil still makes enough magnetic field for something to
Or
happen.
didn't you say that the part that wasn't a coil was, isn't like the part that's not
You guys can begin packing up. I don't want to hear you.
above the coil, the what is it, that part?
And I think this is some iron. It's just not as much as this.
Yeah. Well, then maybe that's why it was.
It's definitely stronger with the core in there. So, all this talk about flux is just to say, magnets weird, they're getting confused. They are fun though. Work on your chapter, your magnetism assignments. Let me know if you have any questions. We'll address them on next Thursday, and then we will start reviewing for test 2, including everything about electricity magnetism. And you have a wonderful, healthy, safe, productive, hopefully plenty of full of delicious food weekend.
Oh, you did say that twice.
Good day.